Hi everybody. We're going to have a look at functions here, and we're going to cover a lot in a little space of time. It's probably one of the more difficult areas of the course, but once you get it, it's not so bad. So, what's a function? Well, let's first of all go through some notation and definitions. The domain are all values that the independent variable can take on. So if we had a function a, it's possible to take on the values 0, 1, 2, and 3. If there was a related variable, b, one that had a relationship with a, when a is 0, in this case b could be 3. When a is 1, b can be 8. When a is 2, b is 4, and when a is 3, b is 10. This dependent variable, which depends on the values of a, in our case here is called variable b. Independent variable here, dependent variable here. Now the possible values the dependent variable can take on are called the domain. The possible values the dependent variable can take on is called the codomain, and the actual values the dependent variable can take on is called the range. So the domain of a is 0, 1, 2, and 3. The codomain of a is 3, 4, 8, 10, and 11. The range b, the range of b, is 3, 4, 8, and 10. It's the actual values that b takes on. Now, once we've gone through those definitions of domain, codomain, and range, we can look at some other notation. Now, there's a thing called a function, and we need to be able to define a function. A function is where for every value of the independent variable, there's only one value of the dependent variable. And one example of that is a one-to-one relationship, so that's like a line. For every value of x, there's a corresponding value of y, and only one value, not multiple values. So here's a domain and a codomain, and we can see here that for every value in the domain, there's only one value in the codomain. So the relationship between the two variables. Now that would mean that this relationship is functional. It's a function. If we look at a parabola, we can see that this is also a function. For every value of x, there's only one value of y. Here we have another one. The interesting thing in this case is that we have a many-to-one relationship. Say for this value of 1 here, it would not only have a mapping to it from 1, but from -1 as well. -1 also maps to 1. I've tried to show that in this example here. You can see that for the number 4, it maps to two different numbers in the domain. That's okay as far as a function is concerned, because every value in the domain still only maps to one value in the codomain. -2 maps to 4, -2 is only mapping to one number. -1 maps to 1, -1 is only mapping to one number. 0 maps to 0, 1 maps to 1, 2 maps to 4. It doesn't matter that 4 maps to two numbers in the domain. It's only the values that the domain map to that's important when defining a function. Now if we have a look at this next example, this is not a function, because this value here, 1, maps to many functions in the codomain. So 1 maps to -1 and 1 maps to 1. An example of this type of function is a horizontal parabola. We can see that this value here doesn't just map to the value up there, a positive value for y, it also maps to a negative value of y. That means that it's not a function. Similarly, a circle, which is a many-to-many function, is also, which is a many-to-many equation, is not a function. We can see here that for this value of x, it maps to 2 values of y. And it's many-to-many because it also does it horizontally. So if we had a value of y, there are 2 values of x. Now there's a simple test that we can use for graphs to show whether something is or isn't a function, and I've drawn this vertical line in here on all of the functions that we looked at, and you can see for this straight line the vertical line only crosses the graph once. That's a function. For this parabola, the vertical line only crosses the line once. It's a function. This vertical line though crosses the graph twice. It is not a function. And this vertical line crosses the circle twice. This equation here is not a function. So when we have a function, we have a special notation that we can use for working with expressions that show the relationship between the dependent variable and the independent variable. Here's the independent variable here. In this case, the dependent variable y is equal to 2 times the independent variable plus 1. That's the relationship between them. And we can find out the value of y by substituting it in here and in here. So in this case, for the equation y equals 2x plus 1, to find out what y is when x is 2, we can say the function at x equals 2 is equal to 2 times, substitute x equals 2 into here, 2 times 2 plus 1, f of 2 is equal to 5. Where the value in the domain of x is 2, the corresponding value f of x in the codomain will be 5. Function notation is really useful and we use it a lot in graphing. One useful thing though would be to set bounds on the domain and the range to say how big, what value can x take on, and what corresponding values will you get in y or in f of x. Now there are some problematic values that we should probably look at first before we start defining what those ranges are and what the domain is. So if we have a look at this function here, we know that for a function y equals a on x, unless a is 0, it's impossible for the function here to be 0. So if you had y equals 2 on x, you can't make that function 0 no matter what you do to x. For root x, or for root x, there's no way that this function can be negative, because if x becomes negative, the function becomes undefined. So y will be positive for all values, and so will x. For y equals x squared, there's no way that you can make a parabola with a turning point at 0, 0 take on a y value of less than 0. These are the sorts of considerations that we're going to take in place when we're looking at domain and range in a second. So if we're not given a domain, we assume the natural domain, so that's all possible values that x or y can take on. So for y equals ax plus b, x can be any member of the real family, and we know that from a line. And similarly, y is any value from the real family. It's going to extend all the way from negative infinity to infinity in the same way that x is going to extend from negative infinity to infinity for a line, unless the line is a horizontal or vertical line, and then there's some exceptions. For the function y equals 1 on x take a, x is a member of all reals. but x can't equal a, because if it did, you'd end up with 1 on 0, which is undefined. Similarly, because there's a 1 on the top, there's no way to make this function into, there's no way for y in this function to be 0. With y equals x squared, even though x can take on any value, it's impossible for y to be less than 0, because once you square the value, even if it's a negative value, it's going to become positive. So here's example 1. Let's do some substituting of values. It's first asking us what's f of 3 given f of x equals 5x plus 1. Substitute 3 into the equation. 5 times 3 plus 1 will give us 16. For g of negative 2, substitute negative 2 into the g equation. Negative 2 squared is 4 plus 5 is 9. If we wanted to find out where f of p equals g of p, take f of x, put it here, put g of x, put it here, and it's asked us to substitute the p's in, which I suppose I haven't done at any point, so I should do that. Let's see. What have I done here? I've taken everything over to one side. Oh shoot, did the wrong thing. So simplifying this down, p squared take 5p take 6. P equals 6 or p equals negative 1. Solved. Now for these ones we want to state the range given for each of these. So if we have f of x equals x plus 1, x is a member of real between 2 to x to 5. So we've been given the domain. We want to look at the domain of this function between real values of x between 2 and 5. So we're not interested in 1, 0, or x equals 6, x equals 10. The domain that we've been given the range of values to look at for x is only between 2 and 5, not including 2, but including 5. So we know that f of 2 would be 3, and f of 5 would be 6. So the possible range of values that we could get, given that this is a straight line, is going to be between 3 and 6, not including 3 and including 6, which is what I've written here. So if we graphed it and looked at it, it's going to start at 2, it's going to go to 5. F of 2 would be 3, and we don't want to include that value, so I've made it an open hole. And at 5, f of 5, or y, is going to be 6, and it's going to include that value. It's going to be the line from there to there. From that we can see that y can take on all the real values between 3 and 6, not including 3, which is what, so from 3 to 6 but not including 3, which is what this range here defines. Y is a member of real for all values between 3 and 6, not including 3. Now if we look at f of x equals root x as the natural domain of f of x, that function looks something like this. Now it's impossible for x to be negative, because if you take the root of a negative value, it's undefined. So here we've stated that x can only take on positive values, as shown by our graph. And similarly, y can only take on positive values. There's no way to make that into a negative value. And that's shown by our graph. Now, this sort of thing becomes easier with practice. Now, if you're wanting to define a function so that you could use it over and over again, It's one of the ways that a function becomes useful, is to use the define function in the interactive menu. So interactive define, here's f of x equals 2x plus 1. If you hit OK, it will write this for you. Now you can type in f of 3 and it would substitute 3 into this equation. You could type f of 5 and it would substitute 5 into this equation, and solves your whole heap of work. And in fact, if you wanted to know when is this function equal to 7, you could use your solve function with it. Solve f of x equals 7 comma x, and it will tell you that x is 3. So when x is 3, this function is equal to 7. Okay, and this is a bit hard to get your head around the first time, but after you've had a bit of a play with it, it becomes a lot simpler than I've made it sound. Have a go at exercise 3A, work your way through it slowly, and that should help a lot. Thanks everyone.